Walk onto the floor of any major manufacturing plant, and you are immediately surrounded by a blur of motion. Robotic arms move at high speed, heavy motors spin continuously, and a dense, interwoven network of pipelines actively pumps fluids. In a single medium-sized facility, there are easily 100 motors driving conveyors, 50 pumps maintaining fluid pressure, and over 200 sensors tracking temperature and vibration, all running simultaneously. Tracking the exact state of every single one of those mechanical assets in real time is a biological impossibility for a human team. The sheer volume of simultaneous physical actions outpaces what our eyes and brains can process. Yet, miles away from the noise, a single operator sits at a desk in a quiet control room, tracking and managing that massive physical footprint across a series of digital screens. The technology bridging the gap between that loud factory floor and the quiet screen is called SCADA, Supervisory Control and Data Acquisition. This foundational data architecture makes operating at an industrial scale physically possible. This raises a mechanical question. How exactly does clicking a digital button on a screen reliably and deterministically turn a physical valve on a distant pipeline? To see how this works, we need to strip away the overwhelming scale of a massive plant and engineer the entire system from the ground up. We will start with one isolated mechanical asset and build out the specific layers of technology required to control it remotely. Memorizing a list of network components is useless unless you understand why each architectural layer is strictly necessary to solve the problem of distance. We begin at the physical bedrock with a single asset that requires monitoring. Let's use an industrial water pump. To know what the pump is doing, we attach field sensors. These sensors detect physical states, like fluid pressure or flow rate, and output a continuous stream of raw electrical signals corresponding to those changes. Here we hit our first bottleneck. A central computer server cannot plug directly into a sensor and read raw analog voltages or electrical pulses. We need an edge translation layer to bridge the physical and digital worlds. This is the Programmable Logic Controller, or PLC, and its long-distance equivalent, the Remote Terminal Unit, or RTU. This diagram maps the flow of information. At the bottom is our physical pump and sensor. The PLC sits right next to the equipment on the factory floor, ingests those raw electrical signals, and translates them into organized, readable digital data packets. The PLC also executes localized control by applying its own internal logic. If the pressure spikes to a dangerous level, the PLC shuts the pump down instantly on its own, without waiting for permission from a central server. The edge layer exists entirely to translate chaotic, continuous physical forces into a standardized digital language that a computer network can process. With one pump connected, we face the next scaling problem. An actual facility distributes dozens or hundreds of PLCs across massive physical distances. To link them together, we build out a communication network using industrial telemetry, creating a nervous system across the plant. Looking at the updated architecture, we scale out to dozens of PLCs connected through that network bus. They all feed into the core of the system, the SCADA server. The server acts as a continuous traffic controller, polling every single PLC multiple times a second and aggregating all that data into one central location. The server then routes that data to two primary outputs. First, it feeds into the human-machine interface, or HMI. This is the visual dashboard that converts the incoming data into readable graphs, trend lines, and active alarms for the human operator. Second, the server routes to the historian database. The historian logs a high-fidelity, time-stamped record of every sensor reading for long-term compliance reporting and performance analysis. But SCADA is bidirectional. When an operator sees a low-pressure alarm on the screen and inputs a command into the HMI to increase pump speed, the flow reverses. The command travels down from the HMI, through the server, across the network, and targets a specific PLC. That command overrides the PLC's parameters. The PLC outputs a new electrical signal to an actuator on the floor, physically spinning the pump much faster. We have now engineered a complete bidirectional supervisory loop. Diagnostic data flows up from the floor to inform the operator, and digital control commands flow down to execute mechanical changes. The strength of the architecture we just built is its strict universality. The top-level software does not care what mechanical equipment sits at the bottom. In a water treatment plant, the physical layer consists of massive tanks and pumps. The edge layer calculates flow rates, and the SCADA server aggregates it to prevent overflow. Apply this to the oil and gas industry, and the physical asset is a pipeline stretching hundreds of miles. The telemetry network tracks pressure differentials to instantly detect leaks across vast distances. In a cement plant, operators use the exact same structural loop to track extreme kiln temperatures and automate heavy conveyor systems. Moving away from moving parts entirely, a solar power plant uses SCADA to monitor inverter health, battery capacity, and total energy generation. And in smart agriculture, the sensors track soil moisture across massive geographical plots, allowing the server to automatically trigger fertigation systems when crops need nutrients. Across all domains, the benefits are identical. Operators gain centralized remote control, maintenance teams reduce downtime, and facilities maintain a much safer overall working environment. SCADA is completely industry agnostic. If a physical asset's state can be measured and translated into a digital signal, it can be integrated into the control loop. Historically, the architectural loop we just built was strictly isolated. The network was closed, and all data lived on a physical server located inside the facility. That isolation is ending with the transition into Industry 4.0 and the Industrial Internet of Things. By deploying edge computing hardware, local SCADA servers are now pushing encrypted data streams securely outside the facility, moving up into the cloud. Plant managers can now monitor live production dashboards globally from mobile devices. Once that data reaches the cloud layer, it is analyzed by artificial intelligence and used to map exact virtual replicas of the facility, known as digital twins. Instead of merely reporting what is happening right now, AI reads the massive datasets stored in the SCADA historian to identify microscopic patterns in vibration and temperature. This enables predictive maintenance. The system identifies a failing motor bearing based on data trends, flagging the hardware for repair days before a physical sensor ever registers a critical high-temperature alarm. This cloud integration provides SCADA with a proactive, intelligent nervous system that predicts mechanical failures before they occur. The fundamental journey remains the same. Physical actions are captured by sensors, translated at the edge by PLCs, aggregated by servers, and rendered actionable on an HMI. Designing, programming, and securing every layer of this complete architectural stack requires highly specialized end-to-end engineering expertise. This is where DEVI Automation Solutions bridges the gap. They provide complete integration across these layers, from low-level PLC programming and HMI development to high-level SCADA and IIoT deployment. Whether deploying heavy industrial automation, rolling out smart agriculture networks, or monitoring solar energy solutions, their engineering teams architect systems built for scale and reliability. If you found this breakdown valuable, please like and subscribe to the channel. To upgrade your facility's control architecture, contact DEVI Automation Solutions today to start building the smarter systems of tomorrow.